All right, controllability. So we've covered the basic mass, we covered the operators, we covered the gradient ascent pulse engineering. The topic for today is under what circumstances can you actually do with your physical system what you want to do. So whether you can, given your controls, given your drift, influence it in the way that you would like. So item 1 is I will remind you what our settings are. So settings, and we have our usual system that is evolving under Schrödinger's equation, and we have the Hamiltonian that is split into the drift and the control part. So we have d by dt of some wave function psi is minus I, then h, and then the function again. And this Hamiltonian is something we can alter, and that is for typically a single quantum system such as a single molecule or a single NV center. If you do have a density matrix, so an ensemble of systems, then d rho by dt is minus I h rho. Right, so time-dependent Schrödinger equation or the Liouville von Neumann's equation. And once again, our Hamiltonian, so h of t, is some part h naught, which we cannot influence, plus a sum over all control channels c, k, t, and then h, k. And in magnetic resonance, these would be magnetic fields. In some electronic state spectroscopy, that would be the electric field, and so on. So this is something that we have as a given, and you've seen the solutions to these equations in the past. In particular, if we have psi of t plus dt, so infinitesimal time increment is the exponential of minus I h of t dt, and then that's psi of t, so that's the elementary infinitesimal time step for the wave function. And since our density matrix is two wave functions multiplied the wrong way around like that, so in order to propagate the density matrix, we need to propagate both of the functions here. And so our density matrix rho of t plus dt is likewise e minus I h of t dt on this side, but also on the other side with a conjugate, so there must be a plus in here, e plus I h of t dt. And we can approximate this and this by taking, instead of the infinitesimal increment, some finite increment of time, assuming the Hamiltonian to be piecewise constant, and there is the foundation of our optimal control theory. So if you look through the previous lecture, so gradient ascent pulse engineering comes on top of this when we discretize the time. Okay, now what we need to find out today is the circumstances under which this wave function actually goes where we want it to go. So item number 2 is, well, firstly, let's just define what controllability is, right? So controllability, and then definitions. Let's think about what we would like to do. In some cases, we have a system in a particular state psi a, and we would like it to move to some destination psi b. So move into some psi b. And if we can do it for any psi a and any psi b, so if this is possible, for any psi a and psi b, and the system is called state controllable. for obvious reasons, because we can go from any state in the starting point to any state at the destination. And I will remind you how we are going from one place to another in quantum mechanics. So remember our initial condition here, and then if we have discretized our time, then we are applying our exponentials, so h, and then that would be h at some discrete time tk, and then the width of the time slice will be delta t k, and then of course we have to apply these slices one after the other, the first slice, then the second slice, then the third slice, so we have a product here over k, and not any product, we have a time ordered product, because these things are in the strict time order from 1 to however many slices we have, and then the exact solution is the limit of all these slices widths going to 0, so lim of delta tk going to 0, and that has another name. This is called a time-ordered integral, and is sometimes denoted like that, exp minus I integral from 0 to some experiment time t, h of t dt. Right, so that's Dyson time-ordered exponential, and that is what it really is. Just slice after slice for infinitesimally thin slices, and then we get where we want to be, and we would like to be in psi b. Psi b. And we will be using this expression in a moment as well. Okay, now the second type, so that would be our first kind of controllability. The second kind is subtly different. Notice here that we say, okay, system is in state A, and we would like it to be in a state B. But we do not put any constraints on what happens to any other system state. We know that A goes to B, but if maybe there has been an admixture of some psi c in there through linear combinations, then it might end up somewhere unexpected, or we don't particularly care where it ends up. So this is one state to one state. What we could do instead is we could say, well, we have specified the fate of every state in the system. So that particular state goes there, this particular state goes here, and all of the other states go to specific destinations. So this is a unitary transformation of the entire state space. So in other words, we need a unitary operator U that transforms the entire Hilbert space. Right? So we have some U acting on our entire Hilbert space and pushing it into itself, but the fate for every state is specified. And then, of course, this U, as you can see, that's literally this, right? Because that is what acts on our initial state. So that U is exp minus I integral from 0 to t, h of t dt. And so if this is possible, the system is called fully controllable. So system fully controllable. Again, for obvious reasons, because we can move every state into specific destinations, including every linear combination of states into the corresponding linear combination of destinations. So if we can synthesize unitary transformations in the fashionable language, these are called gates, right, then the system is fully controllable. Right, so these are the definitions, and there is a disclaimer here to be made. all of these definitions we can realistically use in two situations. So, disclaimer. The dynamics is unitary. Dynamics. So no dissipation. Right? If the system is dissipative, then the controllability questions are not solved in current science. Maybe you will do it. And secondly, no time constraints. So no time limit. Again, finite time controllability is an unsolved problem, so we assume that our system in principle has an infinite amount, well, or rather arbitrarily large, not strictly speaking infinite, arbitrarily large but finite amount of time that is available to you. Okay, with these things in place, let us look at the controllability condition. And really, as useful ones go, there's only one. So item 3, controllability condition. The system is fully controllable. System fully controllable if and only if the set of all nested commutators of the controls and the drift span the complete dynamical Lie algebra of the system. That's a bit of a statement to make. I will have to carefully unpick it now, but essentially the Lie closure of H0, H1, H2 and so on is equal to SUN for an n-level system. So let us pick it apart now and explain what we mean by the various things here. Remember the definition of a Lie algebra. It was a linear combination of operators and their commutators, right? So it was a linear space of operators on which we had defined a commutator. So what we have here is the various operators. Right? So general, so I'd say particulars. The Lie algebra that generates these time evolution operators, so remember the exponentials are a Lie group and the Hamiltonians are a Lie algebra. So the kind of Hamiltonians we can generate are linear combinations of our operators here. Because it's a Lie algebra, not only do we have linear combinations of operators themselves, but we also have a linear combination of all of their commutators, right? So, full algebra that we have is things like H0, H1, H1, H2, but also nested commutators, etc. So we keep calculating those commutators until we get no new operators coming out. For example, if we have Sx and Sy in a single spin, then we commute these two and we get Sz, right? So that would be Sz. But then if we commute any of these three, we will only get themselves out of it. Remember the commutation relations. So we actually have got a complete set of generators in this case of the algebra of a single spin. If you have here a bunch of Zeeman interactions, a bunch of J couplings, a bunch of quadrupolar interactions, here are your magnetic fields. when you start computing all those commutators, eventually the operators will begin repeating themselves. And so you will get the complete set of operators which can enter your Hamiltonian. Right? So that is called a Lie closure. Now, if it so happens that this set of operators is actually the same as the set of all possible operators for the quantum system, then we've got complete liberty, right? By combining these operators and taking the exponentials, we can therefore synthesize an arbitrary unitary transformation of the system because we have access to all of its operators. Right? So if the same as, and what is the algebra of an n-level system? It's SUN, right? Special unitary algebra. So if it is the same as SUN, as the complete algebra of all operators of our system, then the exponentials, right, so the exponential of minus IG, so where G is, let's call it here, G. So that's the Lie closure of our control set. If the exponential of that algebra generates the full SUN, then we can build an arbitrary that's the big one, so the group SUN. Then we can build an arbitrary operator that evolves our system, and therefore we have full controllability. So, full. So that's not an exact proof, it's more of a sketch of a proof here. But once again, if we have a set of our accessible operators, drifts and controls, the set of all nested commutators of it is called the Lie closure of this set. It spans an algebra. If that algebra happens to be the full algebra of the dynamical group of our system, then the system is fully controllable. So in practice, what do we do? So algorithm. First, compute all commutators of the control set, so H0, H1, and so on, until no new operators. Second, compare to SUN. If equal, then the system is fully controllable. Let us go through a few examples, because this is all quite abstract. Let's take a single spin. So item, it will be 4 examples. What do I have in the handout as examples? Okay, single spin. And then X and Y controls. What this means is we have a drift which is just the Zeeman interaction. So H0 is omega LZ. And then we have two controls. H1 is Lx and H2 is Ly. Question, is this fully controllable? Well, it obviously is, because H0 is Lz, H1 is Lx, H2 is Ly. These are already the three generators of SU2 of spin. Right, so the answer is fully controllable. Because the Lie closure of H0, H1 and H2 is actually equal to SU2, which is the dynamical algebra of our single spin. Simply because the three generators are already there, so by combining them and exponentiating them, we can make an arbitrary rotation of that spin, and therefore this particular system is fully controllable. Let us make the problem a little bit harder. Let us disallow the Y controls. So let's say our pulses can only have the X phase when we do magnetic resonance on it. So single spin, but only X controls. Well, let's think about it. We have our H0, which is omega Lz, and we only have H1, which is Lx. But, of course, we have all nested commutators, and we know that the commutator of Lz and Lx is ILY. And so we did get the third generator out of this commutator. We now once again have Lz, Lx, and Ly. So once again, consequence of that is that the Lie closure in this case of H0 and H1 is still equal to SU2, because the third generator turns up in the commutation relations. Well, an even harder problem. Let's only have the Z control. The third one, single spin, and then Z control. This corresponds to having no radio frequency coil at all. So we have the big magnet, and we have some collinear coil to the big magnet that simply just varies the Z magnetic field. So would that be controllable? In that case, we have H0, which is omega Lz, and our H1 is also Lz. So this is what operates in the background, and this is what we can alter. But then, of course, if we take commutator of this and this, Lz commutator Lz is 0. So by taking commutators of H0 and H1, we cannot actually generate Lx and Ly, so the system is not fully controllable. Partially controllable, that's true. We can still, shift Lx into Ly, for example, by turning it, by carefully controlling the magnetic field. So there is limited state-to-state controllability here, but there is no full controllability. Going a bit more complicated here, let us take a look at a two-spin system. And there it's SU2 cron SU2, so you have SU4, and quite a lot of generators that can be in the Hamiltonian. So if we take the first spin, Lx, Ly, Lz, and the second spin, Sx, Sy, Sz, then you also have, as you've seen in your practical, all the direct products between them. So you will have Sx, Lx, Sy, Lx, Sz, Lx, and so on. So SU4, as you can count here, has 15 generators. Unit operator is not a part of a Lie algebra, right? Because we don't have any associative multiplication, and they're only the commutator. So this will be a bit harder to control, as you can imagine. So let us again consider a few cases. If we simply have H0 equals omega Lz plus omega Sz, so two spins with frequencies omega L and omega S, and typically control operators would be the Zeeman operators, so we would have H1 equals Lx, H2 equals Ly, and then H3 equals Sx, and H4 equals Sy. So the various circumstances here would be as follows. If we do not have any interactions between these two spins, like it happens in this Hamiltonian, then it stands to reason that we would not be able to correlate them, so we would not be able to populate these two spin orders. And indeed, if you look at the set of all commutators between H0 and H1, H2, H3, and H4, remember the commutators between those. So Li, Lj commutator is epsilon ij k Lk. Likewise for the S, and operators of the L spin commute with the operators of the S spin, and therefore we can never actually build these two spin orders. So the system is fully controllable on just the spin A, fully controllable on just the spin B, but not fully controllable as a two-spin system because we cannot correlate them in the absence of interactions between them. However, if we do add the interaction term to the Hamiltonian, for example, the weak J coupling, plus 2 pi J LZSZ, then we do have a two-spin order in the drift. When we take the commutators of this two-spin operator with these individually, we will start getting all of those. And so in the presence of the interaction, the system becomes fully controllable if we can influence both spins, but, and I'll leave it to you as an exercise, it is still not fully controllable if we can only influence one spin. Right? So we do need at least the X on either spin, and then the set of nested commutators will generate the complete set of operators. As soon as we have a complete set of operators, we can build an arbitrary Hamiltonian. As soon as we can build an arbitrary Hamiltonian, we can do an arbitrary thing to the physical system, and it becomes fully controllable. Okay, so that's the controllability conditions, a bit academic at this point, until you run into an optimal control problem that for some reason doesn't seem to converge to where you want it to converge. I think Maxi will encounter that at some point. At that point, you'll start wondering, is the amount of control infrastructure I have actually sufficient to drive my system where I want it from where it is? And there you have these various conditions to check. Okay, so the next question that we need to cover today is, okay, maybe we have proven controllability, and so it's a good idea to get going with some optimization and some instrumental process, but to what extent can we actually populate the destination state? If we are sitting at some perhaps electron magnetization, and we would like to move all of it to the nucleus, or we are sitting at some proton and we have, like Jenna's going to have some rubidium or aluminium sitting next to it, and to what extent can we transfer that polarization to some central transition of some horrible quadrupolar spin? So what is the maximum possible efficiency of a transfer, even if the transfer can be made? And that question, again, within the caveats that we have made here on the unitary dynamics and no time limit, does have an answer, and the answer is called Sorensen bound. After Ole Sorensen, who has proposed it in 1989, if memory serves. Now that's a bit of a thing to derive, so let us start with a fairly abstract lemma. So item A, lemma. If we have a vector, vector A, so consider a vector A with elements A1, A2, A3, and so on, such that those elements are sorted. Such that A1 is bigger or equal to A2, bigger or equal to A3, and so on AN, on some n-dimensional space. For us, in practice in quantum mechanics, this is just a matter of choosing the basis set. We simply reorder the basis until the elements of our vector are in this order, and we assume it to be a real vector. Then also, a vector B with elements b1, b2, b3, and so on. Now, of course, it's not possible to find a basis set that would simultaneously have their elements in order, because after all, they are arbitrary vectors. So we've ordered A, but then we are given some other vector B. So, but of course, we can permute it. So the permutation of B that has the largest inner product with A, so that maximizes the inner product AB, is also such that the elements are sorted in the same order. So B1, B2, B3, and so on, Bn. Is again a bit of an obscure statement, but we will see why this is necessary when we start dealing with physics. That is, if we have one vector with ordered elements and another just arbitrary vector, and we are looking for which permutation of this has the largest inner product with A, then that is also such permutation as has these elements sorted. Okay, now let us put this to good use. So B, unitary bound. Consider the following problem. We have some initial state of our system, so A. So now it's density matrices, magnetic resonance. So rho 0 equals A, some initial density matrix. We can always choose such a basis as to make A diagonal, and also to choose such a basis as would sort its eigenvalues. So then pick a basis. Such that A is diagonal and the eigenvalues are sorted in this order. So we will have our A diagonal with the eigenvalues in sorted order. So diag of A, which stands for a diagonal matrix with the elements of this vector on the diagonal, will be the diagonalization of A. And in my notation in the handout, V, A, V minus 1, where V is the matrix that has the corresponding eigenvectors in columns. So we have diagonalized the initial condition, or rather we have simply chosen the basis set in which this is already the case. Then we run the evolution. So run evolution. And here we have an arbitrary amount of time and an arbitrary amount of power under arbitrary controls, so without restrictions. And we will arrive into some final state. So arrive into some final state which will contain a contribution from the destination that we want, so alpha, desired destination, plus a contribution from some garbage which we don't want. And that is probably unavoidable, right? Given a quantum system, that we will arrive to some extent where we wanted to, and to some extent where we didn't want to. So that's the desired state, and that's the garbage. And these two matrices will be orthogonal in the Frobenius norm. So dg trace dg will be 0. And I will not prove that this is always possible, but it is. So we choose our destination and the remaining garbage such that they are orthogonal as matrices. Then our question, or as a Sorensen's question, the one that he had answered, is what is the maximum possible value of alpha? Given complete godlike control over the instrument, arbitrary power, arbitrary time, arbitrary control operators, what's the largest amount of alpha that we can possibly get, given our initial condition and given the desired destination state? Okay, well, let us firstly find out what this alpha is. Alpha, if it's maximum, it maximizes the overlap between the destination and the desired state. So we have started with our initial condition A, then we evolve it, and remember how we evolve density matrices, we multiply it by the propagator and its conjugate transpose on the other side. So that would be some unitary evolution and unitary evolution -1 in here. And if we want the overlap with the destination state, then that's the matrix inner product. So Frobenius inner product, trace. And that would be maximized. And I will note here that alpha is also real because our initial condition is Hermitian, our destination state is Hermitian, our desired state is Hermitian, and in order to maintain the Hermitian linear combination, we need real coefficients in there. So alpha is also real. Okay, now because D is Hermitian, so I would make some observations in here. D Hermitian conjugate is the same as D. We can rotate matrix multiplications under the trace. So trace of some ABC is equal to the trace of CAB. So if we use that and that property here, we will get a trace of, and let me make sure I haven't messed up any notation in here, so that U goes over there, the cross is lost. Now we have U minus 1 DUA. But of course our unitary evolution operator is arbitrary, right? We have assumed no restrictions at all. So we might as well make use of Sorensen's lemma and pick up such unitary evolution as diagonalizes D and sorts its elements again in that order. So in which case what that is going to be is just a diagonalization of D. And we will make the same notation as we did for A. So diag D, so the matrix with sorted eigenvalues of D on the diagonal will be some W dW minus 1, where essentially that's the result of our evolution. And then, well, Sorensen bound tells us that in that case we have maximized the overlap and therefore we have maximized alpha. Notice here that D is not normalized, so we need to normalize it. And so therefore, what follows from here is that alpha max is that, so the overlap between that and that, so that is a D inner product divided by the normalization, so D. And that is what we wanted to prove, and that's called Sorensen bound. As you can see, abstract, hard to understand, unobvious and somewhat weird. All the more credit to Sorensen for deriving this. This bound is very optimistic. Of course, it assumes unrestricted time, unrestricted power, unrestricted control operators, but this is how much you can push a quantum system from a particular starting point to a particular destination in the best possible case, which is still a useful condition on occasion, particularly in quadrupolar spectroscopy. And I'm afraid the rest of this mathematics is all bad news, because there are no settled controllability conditions or bounds that would be general enough to be even covered in this course for any other type of dynamics. If it's dissipative, if you have finite time, if you have constraints on the amplitudes of the controls that you can have, if you cannot have arbitrary controls but only have your electromagnetic fields, then everything becomes case-specific, complicated, non-convex, non-analytical, and there are no further major results, at least at the moment in the literature. But this is why you are here, right? This subject is only just starting. Okay, summary for today. We have our standard equations of motion for the wave function here, for the density matrix there, under a time-dependent Hamiltonian that is split in the standard way into the control part and the drift part. And there are two broad types of controllability. One is called state controllability, where an arbitrary state can be transferred into an arbitrary destination point. If that is true, the system is called state controllable. Or if by carefully choosing your control functions, you can actually synthesize an arbitrary unitary transformation of your state space, then the system is called fully controllable. And of course, in quantum devices these days, at a minimum, we want state controllability for magnetic resonance, and for a lot of quantum devices you would need full controllability because you want to do some data processing on them or some kind of magic with computing. Then the question is, under what conditions are systems controllable? And there is a convenient and reasonably cheap, it's got about quadratic complexity, controllability condition. If you write down your drift and your controls, calculate all of their nested commutators until they stop throwing up new operators, and the list of that operators actually spans and generates the full SUN dynamical group of the n-level quantum system, then your system is fully controllable because you can produce a generator of an arbitrary unitary transformation, which is what we wanted here. And then the algorithm for confirming that is just you calculate all of nested commutators until there are no new operators being generated thereby, and then you compare pretty much just the list of linearly independent generators to the number of such in SUN. If the numbers are equal, then your system is fully controllable. Examples for a single spin. If we have XY controls, we already have the 3 generators of SU2, so that's obviously fully controllable. If we only have X controls in the presence of the Zeeman interactions, then their commutator gives you Ly, and then you also have the 3 generators of SU2, so such a spin is fully controllable. But if you only have the Z field to begin with, and you can only alter the Z field, then you cannot generate Lx and Ly by nested commutation, and so your system is not fully controllable. For a 2-spin system, it depends. If you have 2 disconnected non-interacting spins, obviously you cannot control that entire system, but you can control spins individually. If you want to control the entire system, including spin-spin correlations, then you need to add the interaction, at which point it's up to your luck whether the set of all nested commutators of that and these 4 actually has 15 generators like SU4. If it does, the system is fully controllable. If it doesn't, then it may be partially controllable on individual spin here and there, but would not be fully controllable. And finally, the thorny question of to what extent you can move the system from a particular density matrix A to density matrix B is answered by Sorensen bound, and a fairly obscure derivation. This is actually a cleaned up version. If you look in Sorensen's paper, it's significantly bigger and more detailed. But if you diagonalize your initial density matrix, your destination density matrix, sort the eigenvalues of both in descending order, put them into vectors, take the inner product and divide by the norm of the destination one, you get the maximum coefficient with which you can arrive into this state, and the coefficient is in front of your desired destination. And that is probably the most useful current bound. Everything else is hit and miss, particularly if your dynamics is non-unitary or you have limitations on your instrument output in terms of power, or limitations on the time of your experiment. All right,